Good morning, my name is Dr. Adam O'Donovan. I am a postdoctoral researcher working with the MaREI research group in CIT. Today I will be talking about the outcomes of some monitoring we are completing as part of an SEAI funded study focusing on the in-use performance of air source heat pumps. The study was funded as part of an SEAI RD&D Fund 2018 and is a subset of the broader work that is close to completion on the Design4IU project, which is investigating the in-use performance of energy efficient technologies in Ireland and responds to the need to determine if these systems perform as they should. Today I'll be focusing on three aspects relating to air source heat pumps and the Design4IU project: the published literature, preliminary results from monitoring 5 heat pumps, and the differences between manufacture and measured efficiencies for two technologies, air-to-water heat pumps and exhaust air heat pumps. In addressing these 3 points, I will highlight some of the metrics used to represent the performance and identify the boundaries considered for the calculation of in-use metrics, present some of the in-use performance literature for both technologies, give an overview of the case studies we have been monitoring, as well as show their performance with respect to manufacturers, and finally I will present some of the challenges in comparing these values and present some conclusions based on these findings. According to European Heat Pump Association Statistics Dashboard, there are over 14 million heat pumps installed in the EU to date. There are over 1.8 million air-to-water heat pumps and over 320,000 exhaust air heat pumps. By air-to-water heat pumps, in this case, we mean heat pumps that are used for heating water, for space heating and domestic hot water. These air-to-water heat pumps take energy from the external air. By exhaust air heat pumps, we refer to heat pumps that take heat from the exhaust of a mechanical ventilation system. In this case, the heat pump is integrated into a mechanical ventilation unit with heat recovery. While air-to-water heat pumps don't make up the majority of heat pumps in the EU, they do in Ireland. More importantly, the use of heat pumps and the installation of heat pumps more generally has been increasing by about 12% per annum in Europe, and sales in Ireland have been increasing by 36% in 2019. These technologies have been considered key in decarbonising heat in Europe and have received substantial grant aid for installation in residential buildings. The question is, do they perform as they should? In a theoretical sense, the maximum performance of air source heat pumps can be represented by the Carnot efficiency or Carnot COP. While this value is not practical in reality, it does give an indication as to the upper thresholds we should expect when looking at manufacturer data. Shown in figure 1 on the left, the Carnot COP is clearly impacted by the source and sink temperatures. Manufacturers, on the other hand, report the COP, which is often described as the ratio of the heat delivered on the water side of the heat pump or condenser and the power consumed by the heat pump's compressor. To account for other energy sources as part of the heat pump system, manufacturers will typically report a seasonally adjusted value like the seasonal coefficient of performance, or SCOP. The SCOP is used to represent the performance of a heat pump for space heating only and is an average measurement that shows how effective a heat pump is on an annualized basis. For assessments of energy efficiency in reality, we often use the seasonal performance factor as a metric. The seasonal or system performance factor is an indicator of the real or in-use efficiency of a system. What is of interest with seasonal performance factors is that they can be calculated at different boundaries, which can include the compressor, the fan, supplementary heating, as well as auxiliary devices such as pumps. Table 1 presents the summary statistics of a detailed literature review of in-use performance studies for air-to-water heat pumps by location, year, and estimated system boundary. From this review of 431 air-to-water heat pumps from 10 studies in 10 different countries, the average seasonal performance value is 2.7, with major differences reported between heat pumps. When we look at a national example from the Superhome's final report, we can see that the heat pumps in this study appear to outperform the averages seen in literature. Reductions of efficiency of between 25% and 60% were reported when compared to manufacturers' quoted values. If we sort this table by estimated system boundary, as is shown here, we can see that depending on the boundary we report, there can be different results. This table would suggest that the greatest effect occurs when we move from the H3 the H4 boundaries. For exhaust air heat pumps, these boundaries are seldom reported. Typically, average COP values are given. From this review of 39 exhaust air heat pumps from 16 studies in 10 different countries, the average season performance factor value is very close to that of air-to-water heat pumps. However, the range is quite large. In the study I'm presenting today, there are 5 case study heat pumps. All were monitored at the start of 2020 for a minimum of 2 to 4 weeks in February. However, some air-to-water heat pumps were monitored remotely from January to April of this year, and exhaust air heat pumps were monitored continuously for 8 months from January. All the buildings we looked at were A-rated, modern buildings, and each building had different manufacturers and systems. The majority of air-to-water systems served domestic hot water and space heating, with one serving space heating only. The exhaust air heat pump systems were identical systems, with one in a rural location and one in an urban location. Figures 3 and 4 show the model relationship between manufacturer's COP and external air temperature. For air-to-water heat pumps on the left, the efficiency of heat pumps varies non-linearly with external conditions. If we look at the model relationship based on manufacturer data for exhaust air heat pumps on the right, we can see a very different picture. Manufacturers report a decreasing efficiency with external conditions. The shaded grey area indicates the range of external air temperatures that were indicated during the monitoring campaign. With this in mind, it is our expectation that we are representing the best conditions for air-to-water heat pumps and the worst for exhaust air heat. The data gathered to calculate efficiency metrics was taken from 3 different sources. The first source was from manufacturer-specific software or Wi-Fi adapters. The second was taken from wireless energy monitors installed at the electrical board of each house. And the third was taken from wireless indoor climate sensors, local weather stations, as well as the nearest Met stations. In this study, the boundary that is reported for each air-to-water heat pump is the H4 boundary, which is a system-level metric. This was calculated hourly based on a downsampled data set of between 1 and 5 minute resolution data. For most air-to-water systems, the heat output was calculated based on the condenser side. In the absence of a flow rate or temperature stats from manufacturers, we used the evaporator side to estimate heat output. Where supplementary heaters were installed before the 3-way valve, stats were present either side of the supplementary heater. For other systems, the supplementary heater was installed in the domestic hot water tank. It is worth noting that supplementary heating was not required outside of the activation of Legionella mode that was activated once in every 14 days. For the exhaust air heat pumps, several sensors were installed by the manufacturer as standard. These were utilized to extract the heat output of the device or system at different boundaries. For this system, an equivalent H1 boundary was considered. The unit itself had several modes of operation, which included space heating mode and domestic hot water mode. For this analysis, we will report the modes where the heat pump is in operation and look at points 4 and 6 to calculate the heat output. It should be noted that no active cooling occurred during this period, and we also monitored external conditions. When we examine the scatter plots of external air temperature with respect to COP or seasonal performance factor in figure 8, we can see that each system performs very differently when compared to manufacturer values. Overall, there is a gap between measured and manufacturer values for air-to-water heat pump 1 and air-to-water heat pump 2, where the scale of the gap for air-to-water heat pump 2 is much greater. Contrary to this, the gap between measured and manufacturer values is negligible for air-to-water heat pump 3. Figure 9 shows the same scatter plots for both exhaust air heat pumps. Both systems, it would seem, are appearing to underperform with respect to manufacturer values, and there is a very weak correlation between the seasonal performance factor and external conditions at this boundary. Table 5 provides some summary statistics combining results from literature, manufacturer's performance, and the measured performance from the 5 case studies described. Overall, the results indicate that most air source heat pumps underperform when compared to manufacturers' quoted values, with reductions in performance of between 54% and 63% when compared to manufacturers' values. One air-to-water system performed well in average terms when compared to manufacturer values. When we compare the work here to that of existing literature, it would suggest that the air-to-water heat pumps studied perform better on average. The exhaust air heat pumps, on the other hand, underperform. However, more work is needed in identifying the appropriate reporting boundaries for these types of systems. Based on these results, it would seem that heat pumps are underperforming. As part of this study, we are investigating the application of an in-use factor to correct this underperformance. However, the difficulty in proposing such a factor is that it in itself is a very blunt instrument in reflecting performance. The COPs themselves are calculated in test conditions from standards. Almost all in-use studies, on the other hand, report seasonal performance factors that are not directly comparable to COPs. If we look at an overview of the calculation process from EN 15316 for system efficiency in DEEP, we can see that there is inherent complexities and numerous inputs. The next step for this project is to reconcile in-use measurements with the standards used to reflect performance at design stage. So do heat pumps perform as they should? Based on the results in literature and those presented today, there is evidence to suggest that heat pumps underperform when compared to their rated values. However, the values reported by manufacturers are only as good as the standards that reflect their performance. The performance of the air-to-water heat pumps presented today are favourable when compared to literature and similar to existing studies in Ireland. The exhaust air heat pumps presented underperform when compared to literature. However, more work is needed in identifying the correct boundaries that reflect the performance of exhaust air heat pumps. For us going forward, a challenge exists in how we address this in-use performance gap within standardized calculation. This is critical if we are to improve the robustness of policy decisions and emissions projections. Before I finish, I would like to thank all of those who are part of the Design4IU project to date. We have had many contributions from various parties, those in our team directly and associates of the project itself. Finally, I would like to thank the SEAI for funding this project and thank you for watching. You can find out more about this project by scanning the QR code on the bottom right hand corner. I look forward to hearing from you in the Q&A session. Thank you.